Hi everybody, welcome back. So if you recall from the last video, we finished up, for the most part, building out our power supply. Now there are a couple of more dropping resistors and capacitors, but those will go in as we build the rest of the amplifier circuit itself. So the next thing we're going to tackle now is the output section. Whenever you design an amplifier and you're going to think about the components, especially a vacuum tube amplifier, I like to start with deciding what type of output section I'm going to have and what kind of power supply I'm going to have. And the reason for that is those are the two most expensive parts of a vacuum tube amplifier. Because of course those are the two parts that require transformers, and transformers are quite expensive sometimes. So we dealt with the power transformer. And now we're going to talk in this video about the output transformer. Now, what's the purpose of this? Well, as you recall from the power supply series here, we know that the power supply produces high voltage. And vacuum tubes require high voltage in order to function properly. So case in point, there's 275 volts at the anode of each one of these output tubes, these 6P1s. Now here's the problem. Vacuum tubes require these high voltages to operate, but they can't operate at very high current. So these are what we would refer to as a high voltage and low current device. On the other hand, we have our speaker, and speakers really don't like high voltages. As a matter of fact, they're the opposite. They like low voltages and high current. So what we need is we need a way to convert this high voltage, low current signal into a low voltage, high current signal. And that's the purpose of the output transformer. That's what it does. Now, just like we used this power transformer down here to step up the voltage, and for the filaments, step down the voltage, this is going to step down the voltage. So we're going to take that 275 volts and step it down to somewhere around 10 or 12 volts. And we can actually determine what voltage we need with a little bit of math. I know you guys love the math. I got some comments on that. So we can use some of the information that we know to determine what kind of voltage we need for our speaker. So for instance, let's say this is a 10 watt amplifier, because that's roughly what it's going to be when we're done, I'm going to say, plus or minus a little bit. And we know this is an 8 ohm speaker. So with those two numbers, we can figure out how many volts this is going to have to be. So if we want to know that, all we have to do is we take the resistance, which is 8 ohms, and we times that by the wattage, which is 10 watts, and that's going to give us 80, and we're going to take the square root of that, and you can see we're going to have about 8.94 volts when we're full power 10 watts. Here's the transformer that came with this little kit that we purchased. And of course we got two of these for stereo, and this is one of them. And if we flip it over, they were kind enough to put a little label on there and give us an idea of what this transformer is. So if we look, this is saying that it is a 5K plate to plate. That's what, so it means it's 5,000 ohms impedance. PP means plate to plate, or anode to anode. So what they're talking about is, when we look at the schematic of this, let me back out a little bit, from here to here, this is plate to plate. They're saying that when this is operating, it will act as a 5,000 ohm impedance. Now that is not 100% accurate, because this can change with frequency a little bit. And so everything is kind of a nominal kind of a nominal thing. And it's also reflected back based on what load you have on it. So this side can affect this side, and this side can affect this side. But what we want to do is find out how they came up with this number here. In addition, it also says 4 ohm, 8 ohm, and what that means is on the output, on the other side, the secondary of the transformer, there is a 4 ohm tap, which is this yellow one, and there's an 8 ohm tap, which is this green one. And they're showing the same thing here. And you can see, and I wrote this in. You have your 0, which is the black lead, and that goes to ground. And then you have a 4 ohm tap and an 8 ohm tap. So if you have a 4 ohm speaker, you would connect it here. If you have an 8 ohm speaker, you would connect it here. It's very important to match the impedance of the speaker to the winding or the impedance of the transformer. So you would not want to connect a 4 ohm speaker to an 8 ohm tap, because it will reflect a different impedance onto this side, which will cause more current to flow through the tubes and could possibly damage them. That's why it's really important we never exceed the ratings of the tube by putting the wrong load or the wrong transformer in. If you pick the right transformer, the right speaker, and the right tubes, everything will balance out. If one of these is wrong, it can throw off the whole formula. So a spoiler alert here. I did a little bit of testing on these transformers when I got them, and I don't necessarily think that they are what this label says, nor do I think this is correct. Even on the schematic that it says 5K plate to plate, I actually think that's going to be a problem, because first of all, these tubes, these 6P1s, there aren't really good data sheets out there. There are some, but they're not the greatest. But these are close enough to a 6AQ5 tube, or even similar in some ways to a 6V6, that we can use the data sheets from a 6AQ5. And I can tell you they aren't really specified for this. Usually the bigger the tube, the more power that it handles, the lower this impedance will be. So for instance, if you have one of those massive, 100 and some watt amplifiers that has 4 KT88s or 4 6550s, 2 on each side in parallel, you'll see that this will get lower. This will be maybe 1.5K or 2K or 3K. It'll be a lot lower. And conversely, little output tubes will have higher impedances in some cases, like up to 10K or more. So the recommended plate-to-plate impedance for a typical push-pull design for a 6AQ5 is 8K. So I have a feeling this is not going to be the right transformer. So let's see. I want to test this, and let's see what this really is. So how do we check an output transformer to find out what it is? The ratio between this and this is called the turns ratio. And we talked about turns ratio in our power transformer when we did that in the earlier video. But we are also going to be concerned about something called an impedance ratio. What that means is if we have an 8 ohm impedance on the secondary, how many ohms impedance will there be on the primary? That's what we want to know. We can calculate all this, and it's actually simple math, and it's an easy test to do. We're going to do that in this video. Okay, I think I have all this in frame here. I hope I do. So here's what we're going to need to find out the turns ratio and the impedance ratio. First of all, you're going to need a variac. And you can see I just have a small variac. And what this allows us to do is it allows us to adjust from 0 volts up to our 120 volt mains. And what we're going to do is we are going to turn the voltage up into the primary of this transformer. So we have the variac connected between here and here. And what I'm going to try to do is I'll put some images up on the screen while I'm doing this right now, so that you can kind of get an idea of what the setup would look like. Then what we're going to do is we're going to turn on the variac, and we have one meter, this one on the left, connected to that primary. So it's looking right across this here and our variac that we're connecting. And then I have my second meter connected over to here. Now, if you only have 1 meter, it's not the end of the world. You can basically adjust the variac until you get the reading you want on the secondary, and then move your meter over to the primary and see what you had it adjusted to. But if you have 2 meters, it just makes it go a little bit faster. And for the sake of this video, it'll make it easier for you guys to visualize what's going on here. Okay, let me prop this up because I think I'm getting a little bit of reflection on this meter. How's that? That's better. Okay, variac is on. And I'm going to turn this up until I get 1 volt. I want as close to exactly 1 volt out of the secondary from here to here. Here to here. I want to get as close to 1 volt as possible. All right, so we're going to turn this up and watch this one until we get 1 volt. Getting real close. So there's 1 volt. And that's pretty close to 1 volt. You know, within a couple millivolts. Now we're going to look over on this side, and we see that we needed to put 32 volts. Now, 32 volts in, roughly, to get 1 volt out. So our ratio, our turns ratio, is 32 to 1. So this is going to be what we call the turns ratio. Now this doesn't tell us how many turns is on the primary and how many turns is on the secondary of this transformer. It only tells us the ratio. So there's 32 turns of wire around the core of this on the primary for each 1 turn of wire there is on this, if that makes sense. So that means if there was 320 turns of wire on the primary, there would be 10 turns of wire on the secondary. Does that make sense? So far so good, right? Okay. Okay, that's great, but how does this correlate to the impedance, to how many ohms we're going to see of impedance reflected from the primary to the secondary and back and forth? Well, that's an easy thing to do as well, because all we need to do is we take our turns ratio, which is 32 to 1, and we're going to square that. Okay, so let's say 32 squared, and that is 1024. All right, if that makes sense. Now, we have 8 ohms. So that turns ratio, we have to times that by how many ohms that is. So in this case, it's 8 ohms. So if we take 1024 times 8, you have 8,192. So this is what we would refer to as an 8K transformer. And remember, when we talked about the data sheet, and I will try to put this data sheet for a 6AQ5 and highlight that for you, they're saying that an 8K transformer is the best match for a typical push-pull 6AQ5 amplifier. So we learned 2 things. Number one, we learned that we have the correct transformer for this amplifier. But more importantly, we learned that they marked this incorrectly. It is not a 5K. Now, some of you might say, but Tony, maybe they measured it at 4 ohms, at the 4 ohm tap, not at the 8 ohm tap. Okay, if that's the case, let's put this back how it was. Let's turn the meter back on. And let's do this test with the 4 ohm tap. So I'm now going to move this from here to here. So everything else is connected the same. So we still have the variac going from here to here. But over here, we're going to measure from here to here. And we're going to do the same calculation. So let's turn this on. And you can see with 32 volts going in, we do not have 1 volt coming out in the 4 ohm tap, do we? So let's turn it up until it says 1 volt again. Right? Now, if you look, we have 46 volts going in to get 1 volt out. So now it's 46 to 1 with the 4 ohm tap. So let's shut this off so we don't electrocute ourselves. And once again, 46 squared, 46 squared times 4 ohms, because now it's a 4 ohm tap. Look at that. Which is kind of an 8K, 8.5K. Pretty close. It's still an 8K transformer. So you can see the numbers still work out. And again, there's some little differences in our measurements and things, but it's close enough. So it really doesn't matter which tap you use. It's always going to work out to the same reflected impedance, and that's really the whole idea of the output transformer. And I can tell you right now, if there was a 2 ohm tap and you cranked this side up until you got 2 ohms out of here, and then you measured this and you did the same math, it would still come out somewhere around that 8K. And if you had a 16 ohm tap, you would need less voltage here to get 1 volt here, and the math would still work out to 8K, or somewhere around there. So that's how we determine the impedance, or the impedance ratio of an output transformer. Now here's another quick example. This is a little output transformer. It's a universal one, and this is the type that you would have in a very small low wattage guitar amplifier, or more than likely in a radio, like a tabletop radio or something like that. It's not real high power, you can tell by the size of it. But again, this is a single-ended one. So this one only has 2 wires on the primary. So instead of having a center-tapped primary, where, and we'll talk about this when we get to the output section here, it just has a wire here and a wire here, and you would only use 1 tube. So just think of it as half of this circuit here. And that's called a single-ended amplifier. But we can still do the same test with it. So we connect our meter up to the primary and our variac. There we go. And we, again, this green wire indicates it's an 8 ohm secondary. We'll turn it on, and again, drive this up until we get 1 volt. And we got to get this right on. It's a little jumpy. Pretty close. That's as close as I can get it. So we have 25.7. So let's say it's about 25.5. 25.5 to 1. And again, we do the same math formula. 25.5 squared times 8. And you can see this is a 5K transformer. So this would be for a single-ended vacuum tube, and this one might be something that you would see on, I don't know, maybe like a 50C5 or something like that. Some of them, I think, and I'm pulling this off the top of my head, I could be totally wrong, but some of those small radio output tubes work with a 5K transformer. So it's just as simple as that. That's how easy it is to identify this transformer. Now let's look this part number up if I can, and see if we can see if I'm right. Okay, just look this up, and you can see this transformer is $15.50. And actually, I found this, and I bet you this is where I bought this when I got it, from Antique Electronics. It's an 8-watt single-ended transformer, and look at that. 5,000 ohms into 8 ohms. And this will work with a 6V6 or a 6AQ5 in single-ended mode. How about that? Very cool. Okay, now we know. So anyway, yeah, I knew I purchased this. I got a couple of these, and I just don't remember where I got it, but I got it from Antique Electronics, and that's what it is. And again, I keep a couple of these on hand because, like with those Hallicrafters radios and things, some of them have special output transformers that drive high impedance speakers. And if you want to convert them over to run a standard speaker, you need something like this to do it. And that's why I keep a few of these on hand all the time. Anyway, there you go. It's simple as that. Okay, let's have a little bit of fun. So I've drawn a little diagram of what we're going to do next. And I have a little device called the DATS unit, and it's something you can buy from Dayton Audio, and it's a little module. Mine's the really old version. I bought it years ago. There's a new version they sell now, I guess. It's supposed to be a little better design, you know, with better test leads and that. But anyway, what it can do is it can test the impedance of a device over a sweep of frequencies. So you can start at like 5 hertz and sweep up to 20 kilohertz, and you can look at how that influences the impedance of that device that's under test. So it's a really cool thing. There's a whole bunch of things that you can do with this little module, and it's perfect for what we're going to do here. So I have 2 little test setups. We tested our 2 transformers. If you remember, we looked at the one originally from our little kit, Just a Box of Parts kit, JBOP, and we determined from our math and from our little test that it is about an 8K plate-to-plate impedance on the primary reflected to your secondary winding, for instance, your 8 ohm winding. If you connect an 8 ohm speaker to the 8 ohm tap of the secondary of this transformer, the reflected impedance will be about 8 kilo ohms. So I don't have an 8 kilo ohm resistor, but I do have an 8.2K resistor, which is close enough. And I'm going to connect it on here. Now, normally, you know, you would want to look at this and put an 8 ohm dummy load on this end, but the problem is this DATS unit doesn't have a very strong signal strength. In other words, the amplitude and the power of that signal is not very high. So if you connected to this input that's designed for hundreds of volts, the output would be so tiny here when you're reading the reflected resistance or reflected impedance that the transformer losses and things would actually affect our reading. So you'd get a lower reading than you really should. However, but if we connect it backwards, this is a low impedance winding, and just measure for 8 ohms, If we put an 8K load on there, which would simulate the load that our vacuum tubes should pose to this in the perfect world, we should see a steady 8 ohm impedance on this end across the frequency sweep. And conversely, we checked this other little transformer, this little single-ended one, and we determined that it was a 5K impedance to 8 ohm speaker load. So we're going to use this little tester and check these and see if we do get a reflected resistance. In other words, if I put 5K here, I should see an 8 ohm impedance on this winding. And if I put an 8K resistance on this transformer, I should get an 8 ohm reflected impedance on this winding. So the first one we're connected to is this one up here. Let's move over here. You can see I have two 10K resistors in parallel, so that gives us a 5,000 ohm load, and it is on the primary of the transformer. This would be the side that your tube would be connected to. So this represents the correct tube load that you have on there. This end we have connected to our DATS unit, and it's going to apply that frequency sweep, and then it's going to read back the impedance that it sees on this winding with this load on the other end, if that makes sense. So when you see it up there on the screen, I think it'll make a little more sense. So let's get up here to the screen, and I'll turn the lights off so it's a little easier to see up here. And it comes with this software if you buy this thing. Again, this is not a promotion or anything like that. It's just a device I have that'll do the job we need it to do for this particular experiment we want to do. And maybe I can even get this thing to tighten up. Hold on. Okay, here we go. I will do impedance sweep. And there it is. So on our little transformer, we can see, if I click right on this 1 kilohertz thing, if I can get my mouse on it, we can see at 1 kilohertz it is showing 8.6 ohms. I don't know if we can zoom in on that a little more. So you can see it is showing that that winding is showing about an 8 ohm load if I put a 10 or a 5,000 ohm load on the other end. So it is working the way it's supposed to at 1 kilohertz. But if I back the camera off now and you look, as we go down in frequency, this transformer starts acting less like a transformer and more like a short to that load, until finally when we get down to 5 or 10 hertz, it's only showing about a 1 ohm impedance. And as we go up in frequency, you can see it becomes less of a transformer and more of an open circuit or a high impedance, right? So it's, as we get up to 20 kilohertz, we're somewhere up in the line at maybe 12 ohms or so. So what this shows us is that this transformer only has a linear response in this small area, and then it really starts to drop off. So what that means is this transformer would be good for a you know, for like a guitar amp or something in the mid-range frequency, or for a radio, which is the purpose we purchased it for. But it's really not a super high fidelity transformer, because it's, if this transformer were working perfectly, you should have a straight line across 8 ohms all the way across. And this has to do with the design of the transformer. Now let's move over to our other transformer, the one that came with our kit, and see what it looks like. Okay, so we have our 8.2K ohm resistor connected to the plate-to-plate windings, and we'll take our DATS unit and we'll move it over between the 8 ohm tap and the common lead, and we're going to do that same frequency sweep now. Let me get back up there. Okay, Okay, here we go again. Let's click. And as you can see, this is a much higher quality transformer. So if we look, let's click on our 1 kilohertz again. So if we go right around here, so right around 1 kilohertz, you can see we're right around 8 ohms. It says 8.32 ohms. You can see up there in the corner, 8.39 ohms. And we can get all the way down to 20 hertz. And at 20 hertz, we're only down to about 6 ohms reflected impedance. And if we go all the way up towards 20 kilohertz or close to it, like there's, let's see there, 19 kilohertz, it's still 8.2 ohms. So this is what we would consider a high fidelity transformer, because it can maintain its reflected impedance throughout the entire audio spectrum for the most part. And you can see how it tapers off. And this is, any transformer is going to do this. Now, some of the extremely high quality output transformers that are very, very expensive, they will remain flat beyond 20 kilohertz and below 20 hertz. They'll stay very flat. But this one, for what it is not bad. Now, of course, this is just doing a simple frequency sweep, and it doesn't really force the transformer to deliver any kind of power. So because of the core material of the transformer, the physical size, the permeability of the metal that they use in the core and the amount of it, and the winding and all these things, these parameters will change as you increase the power that the transformer has to move from the primary to the secondary. And what I mean by that is, we have an 8 ohm load on this. As we increase the current and voltage that we're applying to the primary, the transformer with respect to frequency is going to have less and less of an ability to keep that reflected impedance linear. So that's why a transformer not only has a frequency response, but it also has a power rating. So for instance, this transformer, and you can get a rough idea by its size, but this was probably only good for about 10 or 15 watts. As soon as you start getting beyond that power level and you try to demand more energy, that transformer is going to start to drop off. You're going to see it first at the low frequencies, but as you get more and more and more into it, the transformer is going to have less and less of the ability to keep the power level straight. So that's why you also have to get a transformer that's sized for the job that you're going to use it. So this transformer will keep that waveform or that curve that we saw up there for a lot longer, you know, as you increase power, than this smaller one, because this has less actual mass to it, and the actual core of the transformer has less ability to store that magnetic field. Whereas this is a larger core, it has more ability to store a larger magnetic field. So again, it can transfer that power up to higher power levels than this one. So I hope we have a little better understanding of an output transformer and what it does and how it reacts. And the takeaway from this is how to test the turns ratio, and to use the turns ratio that we can calculate the impedance ratio. Once we know the impedance ratio of the transformer, then we also need to know how much power it can handle, if it's the rated power, and how linear it is across its frequency band of, 20 hertz to 20 kilohertz. That's our audible frequency, right? And then we need to know if this transformer is suitable for the type of tube that you are pairing it with. So again, when we look in the tube charts, and I'll put that back up on the screen again, we're going to use our 6AQ5 tube for an example. You will see that they actually have an effective plate load that they want you to have, and that's giving you an indicator of what transformer impedance you need in order to for the tube to operate within its safe operating parameters. If this transformer were the wrong impedance ratio, one of two things would happen. As you start putting audio through the amplifier, either the vacuum tube, the 6AQ5s, would go above their rated current, or they would not be able to achieve their maximum current to get the maximum power. So it could affect the output of the amplifier, and it could possibly damage the tubes if you have the wrong impedance. So that's why this is all important. And I think, again, we can determine that all our tests on this show us that this transformer should be perfect for the application in which we're using it. So it matches, even though they put a typo in there, they show this as being a 5K plate-to-plate transformer. We know it's an 8K, and we know that the tubes that we're using, those 6P1s, which are the same as a 6AQ5, electronically at least, you know, characteristics-wise, they require an 8K transformer. So we're lucky that this tests as an 8K. So I don't know why they put that on there like this, or on the schematic. But anyway, they may have taken that information from a single-ended, because when you use a 6AQ5 in a single-ended single tube like one of these, you want a 5K. That's what they recommend. Anyway, that's it for this one. And in our next part, we're going to build up the output section and test it. And we're going to connect it to our transformer and see how it works. So until then, as always, I wish you all peace, joy, happiness, and good health in your lives. And we'll be back real soon. Take care. Bye-bye.